Okay. Well, actually, I guess this is our last official lecture, though we'll have a lab session coming up this Thursday too. Today, what I wanted to do is fill in on a topic that we haven't very directly covered. I've sort of hit on it sort of indirectly in a few times, but particularly when we talked about things like posterior predictive checks. But this is we'll take a slightly different tack on this, and that's the idea of using simulations based on the MCMC results we generated. Uh, and here I'm thinking of a situation here. We've done our MCMC simulation. So right from the beginning, we're already working in a simulation environment, and we've simulated posterior distributions, or simulated from the posterior distributions of various quantities of interest, usually the parameters of the model but we may have also simulated a few derived quantities. But let's start out thinking in terms of primarily having simulated our the posterior distributions of our various model parameters. But now that we have that, we may want to make inferences about other quantities besides just those parameters. We may want to understand what's the probable range of an outcome, maybe in some new patient who, maybe is described by some set of covariates that are somewhat different than the past patients that we're working with. So we'd like to do that kind of a simulation. Or maybe we want to simulate the probable range of trial outcomes if we were to try various clinical trial designs. So, of course, all of those, all of the possible permutations are not things you would have captured in the initial MCMC run, nor do you want to overburden your WinBUGS runs by putting too many complicated simulations into the MCMC run. So you'd like to have ways of doing some of these simulations after the fact, and that's what we're talking about today. So let's start out with our core premise here. So again, we're starting out. We've got samples whose empirical distribution describes the posterior distribution of our various model parameters, and that's all this statement here is saying. And I just comment here then that the empirical distribution of the posterior samples for our model parameters then approximates the posterior distribution of those parameters, but more generally the empirical distribution of any function of our model parameters then, or the empirical distribution of any function of the posterior samples of those parameters, then approximates the posterior distribution of that function. So that means we can take all of our posterior samples and calculate the posterior distribution for some derived quantities. In particular, one of the kinds of derived quantities we can generate posterior distributions for is the posterior distribution of potential future observations. And in fact, that's often given the special name of being a posterior predictive distribution. So let's talk about some of the mechanics of actually doing this process, and I'll illustrate that in a couple particular contexts. Let's start out with the relatively simple nonlinear regression case, or I guess it's simple regression model. It could be linear or nonlinear, but in particular by simple regression I mean it's not a hierarchical model. We've only got one level of variability, typically referred to as residual variability here, and no other sources of random variation other than the fact that, of course, we've got prior distributions for all of our model parameters. And to make this a little more concrete, I'm going to pick a particular model form, but the things I'll be saying are pretty easily generalized to other cases. So suppose we want to calculate the posterior predictive distribution for a model that has a form like this, where our observations, that we'll call yi, are normally distributed with some mean yi hat and some variance sigma squared. And then our yi hat, our mean value here then, is some function of the remaining model parameters plus some covariates in here. So these could be, could be time, dose, and who knows what else here. Various patient characteristics could make up this xi. So I'm thinking of both theta and xi are multivariate things, or potentially multivariate things. So, and the way we're going to start is we're assuming that we have posterior samples for theta and for sigma squared here. And we know, and let's say we want to make inferences about the probable range of observations corresponding to a particular set of covariates that we'll call xi. Here. So we're going to take a particular xi, we're going to take our samples of theta and sigma squared, and we're going to say what's the posterior predictive distribution for yi. So let's further assume we've got for theta and sigma squared, then we've got our posterior samples, and in particular let's assume we've got n post posterior samples in here. If we think back to the way we've structured that in the R scripts and such that we've used before, inside of R we've always structured these posterior samples as a matrix which contains where the number of rows of that matrix corresponds to this n post. In other words, it's the number of posterior samples, and the rows correspond to the different model parameters. So in what we're looking at here, then we'd have a matrix that has n post rows, and then it's going to have a bunch of columns corresponding to the various components of theta as well as sigma squared in there. So what we're going to do for an algorithm to generate this posterior distribution is for each one of those posterior samples, so I'm saying from m equals 1 to n post here, we're going to do these three steps. First, we're going to go ahead and sample a particular posterior draw from a particular iteration, which we'll call m here. So this theta m represents the theta values, well, we could say it represents the theta values in the mth row of that posterior matrix, and the sigma m is the sigma from that same row within the posterior matrix. We then take those values. I see that I shouldn't be there. Let's get rid of that one. We go ahead and take the values, in this case of theta, from that row, as well as our pre-specified covariates here, and calculate the corresponding expected value, or yi hat. And then finally I plug in that yi hat over here, as well as the sigma squared from our posterior samples, and generate an observation here, this yi from that normal distribution. So now we've got an overall distribution. When we go through all of our iterations, we'll get a bunch of yi's, one for each row of our posterior matrix. So we've now got a distribution, an empirical distribution of our yi values here. And they represent a distribution then that reflects both the uncertainty in all the model parameters as well as the residual variation in our regression model. So let's see, how would we actually do that kind of a thing by using an actual example. So that's actually where our first demo comes in here. Let me shrink this down and pull that up here. That's part of what I had posted shortly before the class on the course website, in addition to the new slides here, was a couple of demos here. They're actually zip files that just contain directories, each of which actually only contains one file, which is an R script. Let's take a look at our first one that I call here Simulation Demo 1. Let's go ahead and open that up. Let me make this bigger and enlarge the... Okay, come on, get bigger. Okay, make that a bit easier to see here. And let me go through a process that's exactly analogous to what we just looked at in this algorithm here. The first bits are mostly bookkeeping here. The example I'm going to use here, in fact, what I'm going to use as the example here is go back to our old first hands-on example that we'd called ME2 hands-on 1. We're going to base the example on that. So let's actually start by going back and reminding you what that looks like. I'm going to scroll all the way back and find it on here. Let's see. There's 2, there's 1. Okay. So let me remind you what that looked like. Okay, so our hands-on 1 example, this is the one where we were looking at the relationship between factor Xa inhibition and plasma concentrations of our drug ME2. We were using data that came out of a phase 1 single dose study, which was a parallel dose escalation design with 8 subjects per dose arm. They had each gotten various single doses of ME2 as listed here. And at various times here, pharmacokinetics was measured in terms of the plasma concentrations of our parent drug, and we had a biomarker here, which was the ex vivo inhibition of factor Xa activity in plasma, and both of those were measured in samples collected at the times listed here. And we had built a model to describe that. This is just reminding you what the data looks like. Oh, and I guess I forgot to mention here what we did in that first example is we looked at the time averaged values of both plasma concentration and the biomarkers. So in effect, we were looking at the average concentration over 24 hours as well as the average factor Xa activity inhibition over 24 hours. Okay, that was the raw data, but when you take those essentially AUCs divided by 24 for each of those, we had a picture that looked like the one on the right. And then we described that in terms of just a simple Emax model here. So you can see we've got our Emax model with normal residual variation on here. I guess it was a sigmoid Emax model. You can see here with this is assuming a value of 0 corresponding to concentration of 0. You can see there's no baseline value on this. So we construct that model. We got posterior simulations then for our Emax, the EC50, and the gamma, and the sigma squared. And that's what we're going to be working with for our demo. Anything else to tell you about? No, I think that's it. Now, if you recall in the original case, we had done this just using the WinBUGS GUI for running it. I went ahead and constructed just a simple R script to run this so that I could collect the posterior samples like we have been for all the subsequent hands-on examples. So it creates created a saved R object containing our posterior samples. So let's go back to, so if we go back to our files, for example, in our ME hands-on 2, you'll see buried in here I've got a directory that's also a subdirectory, also called ME hands-on 1. It's got a bunch of junk, but the key here is it has this one file here that's called ME2 hands-on1.fit.r save, and that contains the all of our posterior samples that we're going to work with here. Okay, so that's the model we're going to work with. In fact, I guess we still have the model open there, so we can use that to point that out. Okay, so the first bits in here are just some bookkeeping. I've got here the name of the original model, the ME hands-on 1. In addition, I've got the name of our the subdirectory that we're working in now for doing our simulation example. It's also the name I used for this file, simulation demo 1. The rest of this is just assigning some names for various paths in here. We get our usual, actually I got stuff here I don't need. I'm not even going to use most of these libraries now that I think of it, but I just left them from one of the other examples. But the real key here, or one of the keys, is going to be right here, where I've built a function for simulating our values. Now, in particular, again, what we want to simulate here, I said we're going to do a posterior predictive distribution for our observations. So what I want to simulate is this, what's labeled up here, this E bar 24 sub I. So that's what I'm going to be simulating. And in particular, I wrote a function that will simulate predictions given a single MCMC sample. In other words, given a single row from our posterior matrix. And here I just called the argument, well, first of all, you can see the function I called fxa.sim. Call it whatever you want. So it's going to be a function. The first argument of our function is going to be a vector containing the posterior samples, and when we actually use it, that vector is going to correspond to one row from our posterior matrix. And then we only have one covariate of interest. It's this concentration here, what's called on here C24. I called it const here, C-O-N-C. So that's the only covariate of interest here. And here I'm saying I want to simulate then the time averaged inhibition of our factor 10A activity. So the first statement here, this fxa hat, corresponds to this line right here. So that's our Emax, our sigmoid Emax model. So you can see the process here. So because the way I'm going to have this, the posterior matrix has named columns, and when I extract a row from it, it'll retain those names. So I can simply use instead of having to use numbered indices here to pick off the appropriate elements of that vector, I can use names. So that's why you see I've got P, and then I've picked off the column that corresponds to our Emax parameter. Then on the right here, I've got my covariate here, const, and then I'm going to raise that to the gamma power, and again, gamma is an element of that same thing, so that's why it says P with the name gamma inside the brackets. Ditto for our EC50 over here. Again, gamma shows up in the as an exponent, and again, concentration raised to the gamma. So that's just our Emax model. So that takes care of our, to calculate our E hat 24 here. And then the next step here is our residual variation component on this. So I've got, and I'm using R norm is the R function for doing simulations from a normal distribution. And then I've got my mean, fxa hat, and then my standard deviation, because in R it uses a standard deviation rather than a variance. So that's our P sigma here. Notice that I am allowing the possibility that maybe you might pass a vector of concentrations rather than just a single concentration value. So this will, and so I put length const in here. So what would happen then is that means if you pass it as a vector of const values, the first line here will actually generate a vector of predicted values, fxa hats, that has the same length as the concentration vector. And similarly here, when I do the R norm, that's going to generate a vector, and it will have predicted values then corresponding to each of the concentrations that you pass. Let's see, is there anything more I want to tell you about that function? Probably not. Certainly ask questions if I left anything out here, something was confusing. So we're setting up that function. Now again, that's only going to be suitable for generating a predicted value for a single column of our MCMC matrix there, posterior matrix, but we'll see below how we use that in another statement then to generate values for each row of that matrix. The only thing I'm doing here is I've specified, actually it's the same parameters that we had monitored back in the original example, and I do that only because for the subsequent work we're going to do, I didn't want to carry along the baggage of a bunch of predicted values and things like that inside the posterior matrix. I only wanted only the parts of the posterior matrix we're going to actually use. The next set of statements here in this block right here is the process of going out to where the ME2 hands-on 1 example was done, grabbing that object here that contains the MCMC samples, and that's what's going on here with this load statement. This load statement is going out and grabbing that particular file. All this hoo-ha in the middle here is just doing things like tacking the appropriate path onto it and giving it the appropriate name, and I've built that up from the stuff that we specified on top. An attempt to make the code a little more general. Alternatively, you could just hard code the exact name and path to that file. And then down here, it's just taking the information. By the way, when you do the load, what you'll get back is that object that we've typically called bugs.fit when we run the run WinBUGS, and it's grabbing the Sims array out of that, and then the next line here is converting that three-dimensional array into a single matrix, so it's just two-dimensional now, and then the last statement is going through and plucking out only the pieces we need from that, only the columns we need based upon what we said up here by the parameters to plot object. So when we finally get down to here, we'll end up, in fact, let me go ahead and let me fire up R. Let me move that over here. And make some of this a little bigger. Okay, so let me go ahead and actually run the first part of this. Right down to where we generate that posterior matrix here. It says it finished. Hopefully I didn't make some mistake along the way. Yeah, it looks like it did. Okay, it went. There's no error statement, so that's good. I just wanted to give you, so this posterior, if you, for instance, you just look at what the attributes of that are using the str function, you'll see it's a numeric matrix. It's got 3,600 rows and 4 columns. And you can see down here the 4 columns happen to be exactly the named parameters that we want here. So that's what that object is now that we're going to work with. Some of this other is just little bits of mechanics here. We're going to go ahead and open up a PDF set of PDF files to contain our plots, because the way I'm going to show this stuff is I'm going to generate this posterior distribution of predicted values, but then I'm going to summarize them as plots showing like posterior medians and then some credible intervals around them. Let me go ahead and do that. Okay, so I'm going to so let's say what I want to do here is we've got this model that describes our effect as a function of these concentrations. Let's say all I want to do then is I'm going to generate posterior samples for a range of concentrations, and then I'm going to what I'm going to do then is summarize them by showing plots. I'm going to show concentration effect plots. and these concentration effect plots are going to show our posterior predictive distributions, but we're not going to show the whole distribution. We'll just show, again, something like the posterior medians and 90% credible intervals. Okay, so the first thing I do here is decide, okay, what concentrations do I want to show these predictions at? And here I picked a range. Here you can see I called it C-min of 0, a C-max of 1600. And I'm going to do that for 201 values. So I'm going to break up that 0 to 1600 into 200 equal intervals. And so here is this DC is just the increment between elements of those. So there, another way to put it, it's the interval width between them. And then this statement here is just going through and generating the corresponding concentration. So for example, if I run that should just take a moment. Yep. If we look at what const looks like, then you can see you've got a bunch of equally spaced concentrations here going from 0 to 1600. There's 201 of them, and you can see they're all the difference between them is 8, whatever our concentration units are here. Okay. The next step is really the business end of this, is right here, this statement right here, where I'm taking my function. Recall that the function up here that we built, just remind you here, so we've got our function here, we called it fxa sim. So now I'm going to come down here, and that function shows up right here in this statement. I'm going to use apply, and if you're not familiar with apply, basically what it's going to do is its first argument, it takes a matrix in here, and what apply is saying is, okay, take this matrix, and depending upon this value, take either each row or each column. When I put a 1 here, it means take each row of that matrix and apply this function to that row. And recall that our first argument was a vector of parameters, and of course when you grab a row from the posterior matrix, that's a row, that's going to be then our vector of parameter values. So it says take each posterior sample here, each row, apply this function to it. In addition, I have to pass remember there was a second argument here, which was our concentration, and over here I'm just specifying as additional arguments here that I need for that particular function. So this one statement here is basically the equivalent to a for loop over the rows of the posterior matrix. Probably the best way to think of it. In R, generally apply statements run faster. They're more computationally efficient than using the for statement, so that's why I did it. I will admit, however, a for statement is a more readable statement than this is. So what this is going to do then, so if we take this and run it, let me select the whole row here. If I take that and run it, which I'll do. So it doesn't take very long for this simple model, so that ran pretty quickly. Now we don't want to look at the whole thing here, but let's see. So this one, let's see, what did we do? So we're actually doing this for each concentration. So if we look at this here and see what's in it, okay, you can see I ended up with 201 rows and 3,600 columns in this case. So each column is actually then corresponds to a posterior sample, and each row corresponds to a concentration. So I've actually got, if you like, 201 posterior distributions in here, one for each one of our corresponding to each concentration value in this. So we've got our posterior distribution for our predictions for a variety of concentrations, but now we want to summarize it. So that's what's going on in this next chunk right here, I'll admit I probably got too many things going on. What I'm trying to do in this statement right here is to construct a data frame that has as columns our concentrations, the information about our predicted factor 10A inhibition values that I called FXA, and in particular I'm going to be, what's going on over here, well, let me point out, because the concentrations you can see on the right hand side, I'm taking my original concentration vector and repeating it 3 times. So I'm going to have, you know, that concentration vector is a set of values, and I'm going to repeat it, I guess, 2 more times after that. So that'll be in there. And what I'm doing in this mess over here is a couple of different things. The first thing I'm doing, because these are kind of embedded within each other, is first of all right up to, let's see here, this apply statement is now taking that remember we've got this pred thing, which is now a matrix where now the rows correspond to concentrations and the columns correspond to MCMC samples. What I want to do is generate some percentiles from those MCMC samples here. So what I'm going to do then is for each row of this, in other words, each concentration, I want to calculate a 5th, 50th, and 95th percentile. And that's what happens if I run this statement right here where I say apply. In fact, if you want to see what that looks like, let's go ahead and just run that piece. Okay, that should spit out. Okay, what didn't I do? Somehow I didn't do that quite right. Let's do that. Try that again. Got to make sure I get the right number of parentheses in it. 1, 2, 1, 2. Yeah. Try again. Okay. Okay, that's messier than I necessarily wanted to put in front of you, but let's go ahead and just look at the top of it here. So it begins right up here. You can see we got a whole slew of columns, and in fact there should be 201 columns. Is that right? Yes, there are. There's 201 columns, and each column or each row corresponds to a different quantile or percentile here. So we've got our, you know, our 5th, 50th, and 95th percentiles in this. And then the rest of it is just reorienting it. Like I take T is taking a transpose of that thing, and then as vector is converting this whole mess to one great big vector. And if you fiddle with that, you'll see that the combination of the transpose and the vectorizing process will put these results in the correct order to match up to the concentrations that I generate up here. So again, that's just bookkeeping. And then finally, I create a descriptor here to say which one of those elements correspond to a 5th percentile, a median, or a 95th percentile. So when I actually run this whole thing together, oh, I guess that ran even quicker than I thought. Okay, it runs there, and let's just look at the top of that. You can see we end up with this thing. Again, this is just the first 6 rows of that thing. You can see you get this column of concentrations, a column of predicted percent inhibition of factor 10A activity, and then another thing indicating what kind of statistic we generated. So here I'm just showing the first 6 components from for our 5th percentiles here. So that's going to serve as the bottom of our 90% credible interval. Let's see, this thing just makes sure they're ordered correctly for the plot, so they're ordered by type and concentration. And then, oops. finally we go ahead and do some plots here. So we'll go ahead and do here I did this one as doing them as fairly simple curves. Actually, let me go ahead and run both of them down to the end to finish off our PDF file here. Oops, did something wrong there. Just go ahead and go right down to the end, run it. It's still going. Oh, I made a mistake somewhere, because I shouldn't be looking at those here. What did I do wrong here? Probably too much monkeying around with trying to do this in real time. Oh, I know what I did. I stuttered when I pushed the button. I pushed it twice. Okay, let me go ahead. You kind of saw them fly by you, but let me show you what we get out of that. So here's what we get. Here again, I'm looking at my time averaged inhibition factor 10A activity on the y-axis and time averaged ME2 plasma concentrations on the x. And I'm plotting then my posterior median and 90% credible interval made up of our 5th percentile and our 95th percentile here. So that's just then giving you I guess it's sort of a subset of the information we have about our posterior distribution. Similar if we go to, the only thing I was doing is showing you two different presentation formats. This one just uses curves corresponding to the different percentiles. This one is doing the same kind of thing, but showing instead putting a curve for our median, but using shaded regions for the credible intervals, in case you wanted to see how you can construct the two different style plots here using lattice plots. Let's see, what else did I want to tell you about that? Now, if you did want to look at, say, a prediction for a particular concentration in more detail, you could do things like that. Let's see, I was trying to think if I hadn't thought about doing that, but I could probably do that fairly quickly where, let's say, for example, you could do, I think this will work. We'll say histogram, and I'm going to say FXA. But let's say I'm going to look at it only corresponding to a particular concentration. So I'm going to say FXA pred, and then I have to select out that concentration. So let's say sin CO and CO. What was the range of concentrations we had here? We went up to 1600 by 8. Well, there must be 800 in there, so let's just 800 must be one of the ones in there, so let's try that. I think that should do it. That's pretty lousy, and I know it's not quite telling the story. Oh, I know what my problem is. I forgot I had done, we've summarized it already. I would actually need to go back to the original. See what I do. I need to go all the way up before we do that summarization process. So I would actually have to take the the corresponding pred values. In here, so that would be slightly different here. So let's see, that would be. Do I really want to try it? We can try it here. We'll say pred, and we'll just have to pick a particular column. Actually, we could say pred CONC equals 800. Now I got to remember, does that have to be a row or a column? Let's see. Trying to remember how pred was structured now. Okay, the rows. Well, I can always make a mistake and fix it later here. I'm forgetting which way it would have been which. let me make the mistake first, I think, and then we can fix it. Oh, that's interesting. Okay, what was it not happy with? It's the trouble with trying to do these things on the fly here. Actually, it would correspond to a different row. Maybe that was my problem. There we go. That's what I was trying to point out here. So if you wanted something richer in description, instead of just looking at a just looking at a limited number of quantiles, if you wanted to see more of a representation of the whole distribution, you could use something like, where do we go? Something like the histogram here, or if you prefer, we could look at something like a density plot. Yeah, which would look like that. So anyway, just the other kinds of representations here. Okay, so that just illustrated then the process of doing this for a simple regression model. The key thing here, this idea that you write a function that can make the prediction corresponding to a particular sample from the posterior distribution. So that's what we did up here. In this section here where we defined FXA sim, and then down here, in order to go across all of our posterior samples, we use the apply statement right here in here, and that takes care of generating them. Everything else was bookkeeping. Okay, so let's move on to kinds of simulations we often encounter in population modeling. And let's see, let me get back down to where we are. Okay. Okay, so let's start thinking about what would we do when we want to do some simulations when we've got models that include a couple levels of variability, and in particular, let's talk in terms of inter-individual variation. So, in other words, suppose we want to calculate, and we'll focus on a posterior predictive distribution again at the moment, and we're going to do that for a population model of the form that we have below, which describes an observation on the ith occasion in the jth individual. So this Yij then, so that's a predicted value again for our ith occasion in the jth individual, and let's for now assume that it's normal, where we've got some mean Yij hat, so that's a mean for that individual on that occasion. We've got a variance here we call sigma squared, and then let's suppose that mean for that individual then again is a function of our model parameters, our thetas here, as well as some covariates here. So we got a Tij, Dj, and drug J. And notice that there's a subscript now on our theta because that could be subject specific. And in particular, let's assume that it is subject specific and that inter-individual variation in that parameter or possibly set of parameters is normally distributed with some mean theta hat and some variance matrix here, omega. So in other words, this is kind of the common framework for, say, a population PK model. So what do we do with that? Okay, well, the algorithm changes a bit because we have to consider we have to consider that inter-individual variation in here. Now again, what we're going to do is we're going to be we're trying to get a posterior predictive distribution, something that describes the possible range of values in some future individuals. And the sampling is going to be like this. We're we're going to have actually two levels of sampling. We're going to be sampling over our posterior distribution, so this is going over all of our posterior samples here, so that's what the M represents. And then we're going to, within that, we're going to simulate it over some number of individuals. So that's where you see for J equals 1 to N pop, where, as I say down here, okay, something I mistyped. Oh no, it isn't. I'm forgetting what I'm doing here. I'm saying here that if you want for these kinds of simulations, when n post is fairly large here, that actually just doing an n pop equals 1 is sufficient for this simulation. You actually don't really need a nested loop in here, but you could do a nested loop. Now this is very specific to the case we're talking about here, where we're going to simulate posterior predictive distributions for individual observations. That will change when we start talking about trying to simulate summaries over individuals in here, things like sample means and that statement will change. But as long as we're simulating only individuals, it's sufficient just to make n pop 1 here. So you could actually skip that extra level of simulation here. So anyway, the first step in here is, again, we need to sample our parameters from the posterior distribution, and for the model structure we just talked about, that's going to be our theta hats, our omega matrix, and our sigma here, our residual variation. So, and those would all, again, if we're thinking of posterior distribution being represented as a matrix, that's going to be, those would all come from the same row of our posterior matrix. Then we need to sample from our inter-individual variation model. So that's why we're going to get our theta j's then are going to come from that normal distribution to describe our inter-individual variation. And then finally we calculate our expected value for the ith occasion and the jth individual here from our model function. And then finally throw on our residual variation as the last step in that process to get our posterior prediction then for a possible jth individual in here. So let's see. So that's just describing the core algorithm then for our posterior predictive distributions. The only substantive change here compared to the simple regression cases, we've added on this step here where we're sampling from the inter-individual variation. Okay, now the thing that I need to often remind people though is, okay, now you've got the posterior predictive distribution from this population model. How do we interpret that thing? Because I've often found it misinterpreted, so I just wanted to make something clear. So let's just actually sort of read through the statements here. So it says simulations from the posterior predictive distribution of individual observations are that distribution then that is appropriate for making inferences regarding the probable range of observations in an individual, and that distribution reflects all sources of variability, let's say here, in other words, both inter-individual and residual, but in addition it also reflects the uncertainty in the model parameters. As a result, the distribution you get is more dispersed. In other words, it has more variability than you would predict for the distribution of observations in a typical population. In other words, another way of putting it is the variability associated with this distribution overall is greater than you would anticipate for the inter-individual variation in any typical population. And in particular, the the variance associated with this posterior predictive distribution will always overestimate the inter-individual variability. The place where you want to use this kind of a distribution, I guess the easiest way for me to think about it is, let's say I was interested in treating a particular patient. So let's say I have a new patient walks in the door, and I want to make some inferences about what would happen if I were to administer a particular drug. So, and let's think pharmacokinetics for now. So let's say I wanted to make inferences about what concentration am I likely to observe at some particular time if I were to give this patient a particular dose level of some drug. Well, given past information about previous patients, I could the posterior predictive distribution based upon those previous patients would be the appropriate distribution to use for making probabilistic inferences about that new individual. What it's not appropriate for is saying what the what the value of inter-individual variance is, because that will generally be smaller than the variability in this distribution. Okay, let's see, where was I going to take you next here? Okay, I'm debating what okay, let's run with that. Okay. So that's what our posterior predictive distributions are for these individual observations. What I wanted to talk about next is a variation on this notion. I'm going to use the term here population simulations, which could mean a variety of things, but I'll use it here to mean a particular thing. And I'm going to use this term population simulation to refer to simulation of what I refer to as a population estimand. And by an estimand, I mean some feature of the posterior distribution for actually, I should be careful. It's some feature of the distribution of values across a population. So, for example, this could be something like a population mean. It could be something like a population percentile, which could be a median or maybe an extreme percentile, like a 5th or a 95th percentile. It could also mean something like the probability of an event or so on. So how do I use our posterior samples for our various parameters then to talk about or to characterize then this posterior distribution for some population estimand like these? And what we'll actually focus on right now will be a population mean, but the concepts we're talking about could be applied to other statistics as well. Okay, and I want to contrast this to simulating clinical trial results or individual observations. So we've actually already sort of talked about getting posterior distribution or a posterior predictive distribution for individual observations. We might also be interested in a posterior predictive distribution for some clinical trial outcome, like maybe a treatment mean from a clinical trial simulation. And again, the thing I'm talking about by a population simulation is related to both, but it's not the same as either. And I'll try and contrast that as we go. The idea here then is we want to use simulations to characterize the posterior predictive distribution of that population estimand, and actually that was a little left over from something that's actually still meaningful, sorry. So a population estimand for some particular treatment, so we might be talking about dose response, we might be talking about dose time response, and so we're talking about a population estimand, like a population mean corresponding to something like a particular dose for a particular drug at a particular time. Okay, so I'm trying to remind me where I was going here. Okay, So we're going to talk about simulations to describe the probable range of our population estimate. And in most cases, we're not going to have a closed form solution for our function of a population estimate. So we're going to be estimating that by simulation. And in a sense, we're going to be talking about two levels of simulation. One where we're simulating over some conceptually infinite size sample of patients in order to estimate this. But in addition, we've got our simulation to deal with the uncertainty in our model parameters on top of it. So here we go. So for each MCMC generated posterior sample of our model parameters, as well as each set of independent variable values like dose, time, and drug, we're going to simulate several replicates of our predicted response at our corresponding time and treatment then. And we're going to do this now for each posterior sample. We're in effect going to simulate a population of people and their responses. And then to get the corresponding estimand, we're going to be using sample statistics for doing that. So we basically simulate the response at a particular time, dose, and drug. And then what we can do then is we're going to calculate our simulated values for our population estimand by using the corresponding sample statistic. So if the thing I want to estimate is a population mean, I simulate as population. I calculate the sample mean for that hypothetical population, and then I can look at the distribution of that across my posterior samples. And similarly, I mentioned here you could do that for things like sample percentiles to estimate the corresponding population percentile and so on. So let's make that a little more concrete by showing it as an algorithm. So and let's see, did I focus? I guess I didn't focus on a particular population estimand, but I guess I did a little bit here. So let's suppose we want to calculate the population mean response at a particular time if I were to administer a particular dose of a particular drug. Okay, and we've got our population model, so we've got our inter-individual variability as part of this. So we start out, our outer loop here is we're going to sample again from our posterior samples for our various parameters. So here we got our theta hats, our omega, and our sigma. So for each element of this loop here, so for each loop I'm going to grab a row from our posterior matrix, and then for each one of those I've got another loop in here. I'm going to go from j equals 1 to what I termed n pop. And unlike the case where we were just dealing with the posterior predictive distribution of individuals, now I want n pop to be something very different from 1. I want it to be large, because what I'm really doing is I want it large enough that I make a fairly small error due to sampling variability. Or as I stated here, it says ideally I want n pop should be sufficiently large that sampling variability is negligible. In other words, we want results that approximate results you would get if you were able to do an infinite sample size. Of course, we can't do an infinite sample size. It's going to be finite. We just want it to be large enough that the error due to the fact that it is finite is fairly small. And of course, we could specify some tolerance for that. So anyway, so we're going to do this I equals 1 to n pop. So now we're basically simulating our population for a particular posterior sample here. So we're going to generate, first of all, we're going to throw in our inter-individual variations. So we're going to simulate n pop individuals and their individual specific parameters. We then calculate the expected value for our whatever our observation is here. And then finally we do our residual variation here. And so we do that. So we generate these NPOP hypothetical patients here, or individuals, in here. So we end that for loop. And then, given all of those values, I calculate an appropriate sample statistic for the desired estimand. And we mentioned, for example, a sample mean. So suppose I want to deal with the population mean. Well, I simply take a sample mean of these Yij's that I generated. So, and that's illustrated here, just doing a sample mean over all of those Yij's in order to get what I termed here this YIM here. So I'm going to get a this sample mean for the for our mth call in our loop here, and we can do that now. Actually, oh, I was pointing out something here. For this particular model, in the special case of a sample mean, I actually don't even need to do this last step here. But for most other estimands of interest, you will have to do that last step in the process. So this is just saying in that special case, it's sufficient to just do the mean over the yi hats here rather than a mean over these, and that's a consequence of the fact that the expected value of this step, right, the expected value over this distribution is yi hat. But more generally, I would want to do something else. For example, suppose the estimand of interest I wanted is the population standard deviation in here, in which case I would have to, in order to get that, I would definitely have to go through and do this sampling step and take the standard deviation, because I would want it to reflect all of the sources of variation, including the residual. Let's see, trying to think if there's anything else I need to tell you about that process. So the key thing here is we've got that nested simulation here. So in addition to the sort of outer level of sampling from our posterior distribution, we also have this process in the middle where we need to generate essentially a population of individuals that we're going to be taking a statistic over. I just wanted to comment here on another fairly common practice, which I suppose might have its place, but I want to make sure you understand it's the distinction between it and actually doing what we just described for doing population simulation. As I say here, for the kinds of models we're looking at, it's been suggested that another approach for calculating a population mean is to substitute the population mean of our patient-specific parameters into the function for predicting a new response. If we look back up here, okay, so that would mean that instead of doing this whole big loop in here, what we would do instead is take a mean of each one of our parameters here. So let me make sure I'm remembering exactly what I want to say here. Yeah. Keep pushing the wrong buttons. Here we go. Yeah, okay, so we would take so instead of doing this process in here as I've shown it, what we do instead is just basically take the theta hat we have for our parameter in here and plug that in right here, and basically skipping doing this whole inner loop that we've got. We would just simply take take our theta hat, plug that in, and the only other thing you'd have to throw in is maybe the residual variation. But as I say, for a sample mean, you'd argue you wouldn't even need to do that. Now that would make the calculation a whole lot quicker, because you would only have one calculation to do for each posterior sample and not have this inner sample in here. But I would argue that that estimand really isn't describing the posterior distribution of that population estimate, in particular the case we talked about. It wouldn't estimate the population mean. It would instead be something you might call as being the posterior distribution of the typical response for an individual, or as I say here, the response for a typical patient, and you could describe the posterior distribution for that, but it would not represent the posterior distribution of something like a population mean, except in a very special case. It would in the case where the random effects enter the model linearly. In that special case, you actually get the same result, but in general, it won't be true. And well, let's see, I guess I was giving it a name here. I said the posterior distribution of that thing. You could call it like a posterior distribution of a typical response. However, if the thing you want to make inferences about is actually, what the posterior mean would look like and make statistical inferences on it, it would not be appropriate. Excuse me, let me knock that over here. Let me make a brief interruption here, and I'll be right back with you. Hello, I'm in the middle of teaching. Hello? Yeah? Yes? Hello? Yes, it is. I'm in the middle of teaching. I just wanted to make sure it wasn't an emergency or something. Okay. Okay. Let me know what goes on then. Okay, I'm back. Sorry for the interruption there. Let's see, where was it going to go? Oh, okay. I guess I was moving on to actually, what am I? Oh, I see. I had the demo here. I'm going to run out of time. I've been talking too much on these things. Let me move fairly quickly through the remainder of this then, though I suppose we could cover some of it during our lab session. Okay, trial simulations. That's another category. We just talked about what I was terming population simulations. Another sort of related notion is trial or clinical trial simulations. And here, that's what I mean by trial simulations is I'm talking about simulations for describing the posterior predictive distribution of trial outcomes. Now, in our population simulations, we were talking about getting posterior predictive distributions for some statistic for some conceptually infinite sample size. Well, now in trials, we're talking about looking at the posterior distribution of, trial outcomes, which often might be something like sample statistics, like maybe treatment means for individual responses. So and as I say here, the simulation algorithm is actually very similar to that for population simulations, except that we want to describe the distribution of outcomes for a finite sample size. So going back to the algorithm here, the big difference is typically that at this step here where we have, in this thing where I have npop, where I want it to be very large in the case of a population simulation, I would want, for a trial simulation, npop will now be whatever sample size you plan to use in the clinical trial. So you actually want then the distributions of the outcomes to reflect the sampling variability that occurs from using those finite sample sizes. So that in many ways is a core difference when we're talking about trial simulations. And this is actually, this algorithm here, if you look at it, is nearly identical. And again, the main difference is that this N arm here then is going to be the number of patients in the treatment arm. Save time, I actually won't go through each individual element because it is essentially identical otherwise to what we were looking at before. And of course, things could get complicated. I show this in terms of a simple function like this, but there may also be other complications in a real trial or even in a simulated trial, such as various things that influence adherence, dropouts and not taking doses when assigned and so on. So those could also be things that might be a bit different than what you would deal with in a population simulation. Okay, let's see what I've got left here to make sure. Yeah, we can at least get rolling on it. Yeah, well, I think we can do the demo because I don't have much more after this. Okay, good. So the demo I'm going to do is I'm going to do some simulations based upon an example we did back when I was showing you how to do modeling of hierarchical models. Let's actually go back to where that is. It was called dose response 1. It was just before. There we go. Okay, so it was an example here. In this case, we were actually, it's essentially a population model, but we're talking about a population of trials instead of people in a way. We're doing a hierarchical model where I had sample mean responses from 5 trials. As I say, it illustrated meta-analysis where we had inter-trial differences. But basically, any place you see inter-trial here plays the same role as inter-individual in a population analysis. So we've got a bunch of dose response data from a few different trials. And the model we had here is just an Emacs model. So you can see Emacs model doesn't even have a sigmoid part. We've got a non-zero baseline here. I guess an extra complication that I'm going to kind of dance around and not agonize over here is it's got a log transform in it. We'll use it. We just won't focus on it here. So we've actually got log normally distributed residual error on this thing. And we've got our Emacs model, and then we have inter-individual, or in this case inter-trial variation in E0 and Emacs. So that's the key difference. We've now got a hierarchical model where we've got our inter-trial variation as well as residual variation, and we're going to want to do some simulations based upon a model with that structure. I think, yeah. So that's we're going to be looking at. Let's get rid of what we were looking at before. Let's go to, close that. Let's go to simulation demo 2 and open that R script. There we go. What did I just do? Where'd it go? Don't know, but I'll open it. There it is. Okay, I ended up putting it someplace other than where I wanted it. Let me reopen it here. Let's try this and I'll do it that way. Okay, let me make it. Let's go to the top and let me make it bigger. Okay, so we've got our dose response 1 model, our original one. Let me again point out, we've got some parameters that we're going to get out of this. We've got we're going to have our means for these. Well, I guess I should point out that our Emacs and E0 are actually log normally distributed. Actually, I need to make sure I actually did that. Yeah, I did that. Log normally distributed, and there's going to be a mean associated with each one of those. Actually, it was written up as a median in the original model that we had. And we're going to do the same thing with Emacs. Okay, so let's just go ahead and look at this. Where are we here? 330, okay. Oh, I named it wrong. Okay. That should have been a 2 there. Actually, I don't think it'll hurt. So that's something that you'll find in the version I sent you. That's actually wrong. Okay, so most of the first part is bookkeeping again. Let's go down, and now I'm going to have two functions because there's two operations we're going to do. Excuse me, I think I've got another quick interruption. I'll be right back with you. Okay, sorry, I'm back with you. Just a few of the downsides of working from home here. Okay, so we're going to do two operations here. One is we're going to look at the posterior predictive distribution of individuals based upon this model. And the other is we're going to look at the posterior predictive distribution for a population mean. So I'll illustrate both kinds of approaches for a hierarchical model. So let's see, we're actually going to have two separate functions here, one that does the individual simulation and one that does the mean, and that's what you see up here. So I've got one called RESP sim and another called RESP mean sim. In here, let's start with the first one. So this is illustrating that first algorithm I had showed for a hierarchical model like this. And what we're actually going to do, in fact, let me show you that quickly again. Let's step back to okay, yeah. We're going to be doing this one where we're going to be doing the posterior predictive distributions for individuals, and remember I said that n pop equals 1 is sufficient, and in fact that's exactly what we're going to do. We'll have n pop equals to 1 in our case. So right down here, so again these functions get called once each time we draw from the posterior. So our argument p here again is a row from the posterior matrix, and then dose is our covariate here. And you can see here the first thing I do is I've got two statements here that are generating values for individual specific E0 and Emax values that are coming from our log normally distributed inter-individual variation models, or I guess technically it's inter-trial again for this case. Then I get the expected value for the response from our Emax model, and then finally I generate samples from our log normal distribution. Notice the way I'm doing log normal is by using normal. So for instance here you can see I do a normal distribution where the mean is the log of our median parameter value in here, and then at the end take an exponential on here to put it back in the original scale, so that happens for all three of these items here. Let's see, so that's going to generate simulations for individuals who get a particular dose. Or I guess again it's inter-trial, so technically it's individual trials. Though I notice I did not put an adjustment for sample size on this, so this in a sense is really generating results for a hypothetical trial of one person, so it is essentially individuals. The next step here is, however, to generate our population mean values here. And this one's a little bit different in that now I'm going to have an inner loop within this, and let's go to that algorithms, remind you what that one is. So recall here I've got this inner loop on this one where this n pop value we want to be large enough so that we have relatively small error due to the sampling variability. So I've got to have an inner loop in which I generate the inter-individual variation component and go through and calculate my values, and then I get out of that loop and then take some sort of a sample statistic of those generated values from our simulated population. So that's what's going on here. Again, this function, this RESP mean sim, we would call once for each row of our posterior matrix. And in here, notice there's an extra argument called nsim. That would be the same as what was called npop in that slide. So generally we're going to want that to be relatively large. And the first thing I do is, again, I generate samples from my posterior, samples from my inter-individual variation. And notice it's almost the same as the corresponding statements in the previous function, except right here. Notice that msim is here rather than a 1 like we saw before. And then down here, I actually do a loop where I'm going to down here where actually what I'm I gotta be careful with my statements here. So this statement is essentially that loop process, because here I'm generating nsim values here and nsim values there for individual specific things. Then inside here, well, first of all, this loop is actually looping over dose in this case, because I'm allowing for the possibility that this dose might be a vector of values rather than just a single dose level. But inside here, I generate, here I'm doing the expected values in here, but notice that, remember that E0 and Emax now are vectors of nsim values in here. So for each dose, I've got nsim there, nsim values for the Emax in here. Well, ED50 I don't need to because that didn't have inter-individual variation on it. So when this is done, I will have, for each dose level, I'll have nsim values of our simulated expected value, our RESP hat here, and then I'm going to then simulate right inside this statement here. I've got my log normal distribution to generate the corresponding nsim predicted values, and then finally I take a mean of all of those things. So all of those things put together, where you see all the nsims, are basically serving the role of that loop that we saw on the slides. So when I finally spit this out, what it's going to spit out is it's going to be one population mean for each dose level corresponding to a particular row in our posterior distribution. Then we've got, again, I pick off only the parameters I'm going to be working with. And here I load up the results. So I go back again to the corresponding model, in this case the dose response model, the dose response 1 model, grab the posterior samples here, reformat them into that posterior matrix. In fact, let's go ahead and run. So let me actually clear the mess from the previous run here first. Okay, so let's go ahead and run the first part of this. And let's see, let's go ahead and load it all the way into grabbing the posterior here. I'll take a moment to pull all of that in there. By the way, I realize I'm using a different interface than I think I've usually used in the course before. Usually I was using the, okay, got some errors, we'll get to that in a second. I was usually using the, Oh, I just realized what I did. Never mind. Sorry, I've got too many threads going in my head. I'm using a different interface here because rather than using the Windows, I'm actually working in the Mac. But I figure you're used to seeing some of this other stuff enough that it probably doesn't matter which text editor you see stuff in. I just realized I know what I did. I changed something that I really didn't want to change. I do want this to be dose response 1. I wasn't thinking when I changed that. Back again. Okay, let me rerun that because I think that's caused all the errors that we had here. That went too far. Just down to here. Let me clear this junk out of here. Okay, what did it just do? Something funny happened here. I don't know. Well, rather than waste time trying to solve it, let me start it over. Okay, again, let me make it bigger. Maybe a little too big. Okay. Okay. Let's try again. Okay, I don't see any errors that time. I think we're okay. Let's make sure we got something that makes sense. Let's see, it looks okay. Let's see, we've got our 2, 3, 4. Okay. So you can see we've got our posterior matrix then, so it's got 3,600 rows here and 6 parameters here, 6 columns, so we should be okay there. In fact, let's make sure it's the column names we wanted. Okay, I think that's everything we need. Let me go down and let's see if the rest of it works. Oh, actually, let me show. I just realized I hadn't shown you some of it yet. So we've got that. So now what we're going to do down here is similar to what we did with concentrations before, where I just specified the minimum and maximum and then how many I want. I do the same thing here for doses. So I'm going to make predictions for going from 0 up to 80 milligrams, and I'm going to break that up into 40 intervals here. In other words, calculating 41 values over that equally spaced. So that's what's going on here to calculate those various doses. So if I do this here, okay, so if I look at dose, you see I get a bunch of doses here spaced 2 milligrams apart going up to 80. So down here, first part is where I'm going to do the posterior predictions for individuals. So that's where I use that RESP-SIM function. So this is just like we did before in terms of this, because the steps we take at this point are essentially the same as we did before. Where the real differences came into play is inside the function. So inside the RESP-SIM function here, we have the steps in here to do inter-individual variation, but other than that, things are pretty much the same. Let's go back down here. Let's see, what did I actually run so far? Okay, down to dose. So we can go ahead and run that, and we'll get pictures similar to like we saw before, except for a different model, of course. Okay, that takes a minute to run. Actually, the second one I can't show you yet until we do another one, but I can at least show you the first. So, oops. Okay, so you can see here what we're getting then is, again, remember what it is. It's a posterior predictive distribution for individuals. So theoretically then, this is telling you about the, given your current state of knowledge, if you were to ask, okay, if I was to give the next patient 60 milligrams and I don't know anything else about them, what's the probable, what's the probable range of responses I would see? And so you would just sort of go up here and look, and you'd see that they'd go, I don't have enough breaks here to tell. I guess it's roughly from around 7.5 to about 15 or 16 up here. There'd be a 90% chance they would fall within that range. But again, you get your median and 90% credible intervals about that. So let's go to now our simulation of a population mean in here. And again, actually a lot of it doesn't look a lot different because again, the details are handled inside the function. Most of the rest of the steps you take look pretty much the same. In fact, they are pretty much the same. Again, now you have to specify this NSIM. In this case, I just kind of arbitrarily picked 1,000. Now, whether 1,000 is sufficient to get the kind of error tolerance you want is something you might have to check. But that's what I picked just off the top of my head here. It might not be sufficient. You might have to go bigger. So we can go ahead and run that. Now that one, in fact, I'll go run that by itself. You'll notice that that one takes a little longer here because we have that inner loop in here. So we've got, well, if you think about this, we've got, what just happened here? Let's try that again. Okay, it's being weird on me. Let's try it again. There we go, I think. I don't know why it says finished evaluation, though. Hopefully it's running. This one always takes, well, you can see the caret hasn't come back here. So this always takes a while because keep in mind you have, first of all, 36 outer iterations in the outer loop, and then you have 1,000 per each one of those. So what do we got there? 3,600,000 calculations in a sense going on in here. So it's a fairly large number. So it does take a little bit before we get to the end of that. It looks like it's happy. So assuming I didn't make any other errors in here, the rest of it we should be able to pull together and get plots. And it looks like it finished. Let's make sure we don't have any error statements. We don't. So let's go back and take a look. Let's go all the way back to the beginning. So again, here you've got your simulations for the posterior distribution for a posterior predictive distribution for an individual. The next picture is the same thing, just done using the shaded regions instead. And this is what the population mean, or the posterior prediction of the population mean looks like. So, you sort of look at this is very wide, that's much narrow, and of course that's what you expect because this no longer reflects the inter-individual variability. Both the inter-individual and residual variability have essentially been canceled out by the process of taking the sample mean over the population. And so what this reflects then is the uncertainty in our model parameters at this point rather than any of the variability. So again, this is reflecting both inter-individual and residual variation, whereas this is reflecting only the uncertainty in the model parameters, and thus why it's narrower. And again, you can do that as a using the shaded regions in here. Okay, let me take a. We're approaching the end, but we're just about there. Let me take a quick breath and see if there's any questions before I move on to your homework assignment. Let's see, nothing apparent yet. I'll keep my eye open there. Let me, I think the next slide I had here was to look at the assignment. Oops, let me get rid of that. Yep, okay. So what I was going to do is have you do essentially what we were doing in the last element in there, is to do a few simulations based on MCMC samples, and the okay, where did I do it? Did I? Oh, I very cleverly didn't write something on here that I needed to write on here. This one I definitely did just before. Okay, the idea here is to take the ME2 hands-on 2 example and do some population simulations based on that. And in particular, what I was going to say is take that. Let's have you simulate the posterior mean. The posterior mean and 90% credible intervals for the population mean effect versus time, and do that for each dose level. And then the second part is to do the posterior mean and 90% credible intervals for the population mean effect versus concentration. And in this case, you don't stratify it by dose, just do that for the overall concentration effect relationship in here. Notice that, let's see, does it? No, never. Actually, did I? No, that's still right. Okay. It took me a moment to think about something. So we want to do those two cases. Do it for basically all the doses that were in that study for the ME2 hands-on 2 example. So they're listed here. And for our ME2 concentration range, make that from 0 to 1600. I forget our units. They were probably nanograms per mil, but I don't remember. And summarize those results as plots showing, actually, notice I confuse this. I say mean here and I say median here. Why don't we call these two medians here? I'll try and fix that on the copy of the handouts I have on the board. I'll try and remember that. So you do posterior medians and 90% credible intervals by time or concentration is appropriate for these two cases. Of course, if you want to explore some other simulations, you can look at things like the posterior predictions of individual values and maybe some other kinds of statistics if you like. But these are the ones I'm actually assigning and that we'll go over on Thursday. The other thing I guess I should mention is so this is the last week. So for those of you that are going to do some of these for credit, you should be working on your projects. In fact, I forget what we had stated on here. I'll have to look again. I don't remember what we stated as far as the due date, but there was a certain period of time after the the end of the course, when those should be turned in. In addition, there will be a final exam. I still haven't pulled that together yet. I will attempt to do so by the end of the week, and set a suitable duration of time to do that. For any of you that plan on doing it and for some reason the scheduling isn't working out because of holiday trips or some sort of thing, let me know. I'm sure I can be reasonably flexible about that. Other than that, I guess see if there's any last questions, and plan on joining you again on Thursday. Let's see, what do we got on? Let's see. Well, I was, but I actually, as I was saying, I couldn't remember when it was. So it is posted, I believe. Actually, you know what? We might even have it in the slides. Let me see if I can find that real quick. If not, I believe it's posted on the site, but I can try and get that for you later. I just don't remember it off the top of my head. Let's see here. Okay. Oh, okay. No, I guess I had that later. I guess I did post it later, didn't I? Let's see. Yeah. Okay, here we go. Okay, I guess I don't have this in here. I will make a note for myself now to post that. I thought we actually did have it specified somewhere here, but I'm not spotting it in the notes right now. And thanks for the compliments, Mike. So I'll plan on, I will be here on Thursday then to follow up on the homework assignment, and I guess look forward to it then. See you now. See you till then. Bye for now.